How's it going, everyone? In today's video, I will be discussing, then solving the 11th Damn Vulnerable DeFi challenge, Backdoor. Like with the past two videos in this series, I will be analyzing the code of the contracts that make up this challenge for the first half of the video, and then show you how to hack them for the second half. To incentivize the creation of more secure wallets in their team, someone has deployed a registry of Gnosis safe wallets. When someone in the team deploys and registers a wallet, they will earn 10 DVT tokens. To make sure everything is safe and sound, the registry tightly integrates with the legitimate Gnosis safe proxy factory and has some additional safety checks. Currently, there are 4 people registered as beneficiaries: Alice, Bob, Charlie, and David. The registry has 40 DVT tokens of balance to be distributed among them. Your goal is to take all funds from the registry in a single transaction. Now, let's take a look at the wallet registry contract that we need to hack. Inside the constructor, we initialize a master copy and wallet factory addresses, as well as the token contract. It also loops through the initial beneficiaries array passed into the constructor, passing each beneficiary to the add beneficiary function. The add beneficiary function is a public function that only the owner can access, which by default is the deployer of the contract. All this function does is modify the address to Boolean beneficiaries mapping by assigning the return value of the beneficiary key to true. The remove beneficiary function does the same thing, except it assigns false to the return value. The proxy created function is a last function inside this contract, and it is executed when the user creates a Gnosis safe wallet via the create proxy with callback function inside the wallet factory contract, setting this contract as a callback. The function takes as input the Gnosis safe proxy contract, a singleton address, which is just the Gnosis safe wallet master copy address, and initializer bytes data, which contains the call data that was called to the wallet right after it was created. The function first ensures that there are enough tokens in the registry to pay the beneficiary. Then it initializes a payable wallet address variable, assigning it the result of casting the payable operator into the proxy contract. Next, it ensures that the caller is a wallet factory and the singleton is a master copy. Then, it checks that the initial call data was a call to the setup function in the Gnosis safe contract, and that the wallet was initialized with the correct max threshold and max owner's values. It fetches the wallet owner from the wallet contract and then ensures that the wallet owner is a beneficiary using the beneficiaries mapping. Lastly, we remove the owner as a beneficiary. The wallet owner's wallet address is saved to the wallet's mapping, and the tokens are paid to the newly created wallet. If you're interested in solving this challenge on your own, I'd recommend checking out the Gnosis Safe Wallet contract linked here, and the Gnosis Safe Proxy Factory contract linked here. Okay, pause the video now and try to solve it, because in just a few seconds I will present my solution. Here's the solution. We need to deploy a malicious contract with a function that creates a wallet for each of the beneficiaries by calling the create proxy with callback function on the factory contract. Once the wallet has been created, this function will call the wallet using the initializer data passed into it. Specifically, the initializer data needs to call the setup function. The input for the to argument needs to be the contract address for a delegate call, and the input for the data argument needs to be the encoded function data for a delegate call. The to address will be the malicious contract, and the data will contain an encoded call to a function within the malicious contract, which approves the contract to spend the tokens that the registry will pay to the wallet. If you are not familiar with what delegate call is, it's a low-level function that allows a contract to execute the code of another contract's function inside the context of the calling contract. If you are still confused, it will make more sense once I go over the malicious contract source code. Here is what the malicious contract looks like. Inside the constructor, we initialize the addresses of the same contracts initialized in the registry contract, plus the address of the registry. This attack function takes as input an array of all the beneficiaries in the registry and loops through each beneficiary in the array. Inside the for loop, we initialize a new in-memory array of length 1 named owner that stores at index 0 the element at index I in the beneficiaries array. Next, we declare an initializer variable of type bytes, assigning it the encoded call to the setup function on the Gnosis safe. The way we encode the call is by using the avi.encode with selector operator, passing in the function that we are going to be calling, followed by all of its parameters. The first parameter accepts an address array of wallet owners, so we pass in the owner array defined here. The second parameter specifies the threshold number, which will be 1 for each case, since that's what the wallet registry requires. The third parameter accepts the contract address for the delegate call, which is this address. The fourth parameter specifies the encoded callback data for the delegate call, which in this case we will be telling the wallet contract to execute this delegate approve function inside the context of the wallet contract. Instead of calling it inside the context of this contract like a normal function call, the wallet executes it within its own context. Therefore, the contract that will be calling this approve function on the token won't be this contract. It will be the wallet contract. We pass in this address as a spender so that the wallet will approve this contract to spend its tokens, and then we pass in the token address. We don't need to pass any useful data into the last 4 parameters, so we will just pass in default values for each. Now that we have defined our initializer call data to the newly created wallet, we can now call the create with proxy callback function on the proxy factory and assign the return proxy contract to a variable. We pass as inputs the master copy address, the initializer data, and any salt nonce. I'm just using I, but you could use whatever. And for the callback, a proxy creation callback contract instance that has the address of the registry. Lastly, we transfer the tokens from the proxy wallet address to the attacker, and we repeat the whole process for each of the beneficiaries, effectively draining all funds from the registry in a single transaction. For the last step, we'll write a script in this backdoor.challenge file that deploys our malicious contract, then executes the attack function on it. All right, let's run our exploit. Sweet. As you can see, our exploit was successful. We have taken all tokens from the registry, and each user registered a wallet and is no longer registered as a beneficiary. If you enjoyed this video and would like to see more Web3 coding content, please leave a like and subscribe. It helps the YouTube algorithm recommend my channel to more people interested in learning about Web3 development. Until next time.